Thank you for stay this long. This is practically whole day, and there has been a long day. I think we need one more. So the panel discussion leader will be Dr. Pushkar Apte. He's a Vice President of Technology Programs at the Semiconductor Industry Association. He spent 5 years at Texas Instruments, where he worked on cutting-edge research and technology development, and 5 years at McKinsey and Company as a global semiconductor expert. So he has a lot of expertise. He has knowledge on global business strategy issues in semiconductor industry. His also work focuses on intensifying university research on long-term technology issues. He got a PhD in electrical engineering and materials science from Stanford University. So with that introduction, I will ask Dr. Apte to lead the discussion. Yes, thank you.
Thank you very much, Dr. Kang. Thank you everyone for inviting me here. First of all, I need to apologize. I was not able to come here in the morning because I had a conflict that I couldn't avoid. So I missed some of the excellent talks, but I caught all the afternoon talks, which was very good, very interesting. I think the amoeba thing was a different one. It was interesting. And pardon me if my knowledge of Memristive systems is not that great. I read the E Times paper and so forth, and as I was thinking about it, I thought that, I don't know if it was covered in the morning, but there's one Memristive system that everyone seems to have missed, which is our current financial system. The more investment banks that go down, the more the resistance to flow of capital, right? Is that a Memristive system? So I think that works. So, and as Professor Kang said, I have some background on the dark side, on the business side, so I thought I'd come up with an example like that. With that, I'm very, very privileged to be with this very distinguished panel who all know a lot about Memristive systems, and Jeff and I work very closely together. He's the director of NRI, which is one of the SI and SRC programs. So since our time is really short and I know everyone's at the end of a long day, I thought what I would do is maybe put all the panelists on the spot and ask you to give your 30-second or 60-second elevator speech on what you think is the one or two greatest things or the most different things about memristors and memristive systems, and then open it up to questions. So I don't know who wants to go first. Here.
That's fine. I can use this. Okay, so obviously I haven't given a talk earlier. Just as a quick background, the NRI is the program that Wolfgang Perode was talking about for future electronics, looking for something that can scale beyond CMOS for digital systems specifically. And I would say that the thing that I find the most interesting about the memristors, I'm not sure what their application might be in terms of the purely digital computation space, but I think it does touch on several things that we think are quite important if we're going to find anything that is going to go beyond CMOS, which is it's probably not going to just be building new NAND and NOR gates, because NAND and NOR gates are quite efficient in CMOS, and to beat them is very difficult. So it probably is going to require a different way of doing computation. Whether it's material implication or some other method, I don't know yet, but I think it does require that thought. And we find that's the most challenging thing to get the researchers to consider, is not just building another NAND or NOR gate or just augmenting CMOS, or for that matter, just building another FET. People oftentimes bring forward proposals with nanotubes that are just FET nanotubes, which may in fact be quite useful but aren't going to go significantly beyond CMOS. So I think that's one of the most important things about this type of device, is when you find a new device function, it hopefully forces you to think about what architecture would actually be useful for getting computation out of it. Obviously, I'm concerned about digital, but analog computation or other applications are also important. And the second point I'd make on it is I like particularly the last talk where it was talking about application-specific uses. I think that for anything we find that's going to help us continue computation far beyond wherever CMOS stops scaling, it's likely to end up being more application specific than we've had the pleasure of using CMOS for. The digital NAND and NOR is extremely useful across a very broad range of areas. It's not necessarily the most efficient way to do any of them, however, but it's been good enough, cheap enough, and keeps getting better every year. So we've been, I guess, fortunate enough to be able to be lazy and just continue to use it. As that stops doing that, I'm sure we'll be challenged to actually think about how better we could actually do some of these applications. Are there algorithms that are better implemented using different structures? So I think those are the two things I think are most important about the Memristor systems in terms of the kind of thought they drive, hopefully for future systems.
Okay, so now my 30 seconds. Okay. Okay. Yeah, as mentioned, I would say the scalability is really the prospect of Memristor system, and Memristive devices. And that applies to a range of systems. I've shown two examples where you can really go down to the nanometer, the sub 10 nanometer scale, perhaps sub 5 nanometer scale, which is much below what we can conceivable see for CMOS. That's certainly the biggest issue which you can see for memristors. On the other hand, we have to be aware of the fact that we are only at the beginning, because although many people somehow, mainly phenomenologically, have worked on different systems without knowing that they are working on memristors at this time, we do not have any full understanding of the material, and having, as I said, mechanistic-based design rule set, which leads us in guiding through the treasure map of the materials. So out of the materials which are conceivable, only very few have been touched, and that's mainly just by phenomenological thoughts and not by scientifically guided rules. So there's a lot of things to be done. Thanks.
I essentially look at this area as both tremendous opportunity and challenges. As I mentioned this morning, memristance, semiconductor memristance, emerges when you get into this nanometer scale. And so the reason why it's been popping up all over the place recently is because we're now working at that scale. So it's a fact of life. It's here, and it's becoming dominant in a lot of systems. And so we have to deal with it, whether we want it or not. It's something that's that is either has to be engineered out or engineered into our systems, one way or the other. I think that what really brought this home to me, and I mentioned this issue about, we're always talking about how the nanoscale is different. Well, how the nanoscale is different for semiconductor memristance is only a couple of volts bias across a couple of nanometers is a huge electric field. And in that huge electric field, you wind up having some interesting coupling that goes on. And so, for instance, in many of these materials, the dopants start to move. And when the dopants move, that affects the way the electrons move. And it's that coupled, or that coupling of degrees of freedom within the device that I think is truly a nanoscale phenomenon, because otherwise you wind up with very large voltages and other things going on. So it's this coupling that you get at the nanometer scale that provides this, this opportunity that we have. And so looking at it more broadly, I think that it provides opportunities for research as well as opportunities for technology. But the research, first of all, we're going to have to do a lot more materials work, because right now there's a journal of solid-state ionics and there's journals of solid-state electronics, but those two group communities don't talk to each other, right? And so we have to couple those together in materials research. Then there's device-level research, because in fact, you can start getting very interesting behaviors when you think about the similar types of things that you would do with ions, as we've been doing for decades now with superlattices and other structures for doing band gap engineering. And so now you're starting to, if you think about moving the ions around in heterostructures or in layered materials, that's going to bring, I think, a whole range of new types of electronic devices that we've never even thought about before. Devices that are at the nanometer scale that have properties that you know, have never been obvious to us. And then, of course, we have to figure out what we're going to do with those. Then there's the circuit level of research. So there's a lot of research at these three different layers. And then, of course, it's going to be some bright young person who comes up with the perfect application and decides, you know, what's going to drive the whole thing. But I truly believe that memristors have the capability and the capacity to essentially start off a new round of what we might call a sort of a second generation Moore's law, essentially a new S-curve, if you will, in which we're just getting more bang for the buck in terms of more capacity per unit area on a chip and per unit of power that we expend on that chip.
Yeah, following up on this, in fact, the memristive idea, you know, puts it. I mean, it gives a totally different perspective on many physical processes, both in solid state devices, and I would say also most importantly on biological processes. In fact, if you look around in biology, you would probably see that many of the things that occur may be mapped into memristive behavior, like what I was showing today with the amoeba. And that is an opportunity that goes way beyond, in fact, solid-state physics, because you can actually learn a lot from biology and bringing it into solid state, and vice versa. You can use concepts from solid-state physics and try to understand biological processes. So this is an interface that has not been explored, I would say, between memristive solid-state devices and biological processes, which gives us a lot of opportunities beyond what has been said.
Well, it's getting late, and in order to get to the discussion, I don't want to repeat what I said before. I mean, it's pretty clear. I think there's going to be lots of interesting work that's going to happen in this area, and if I may add on the lighter side, I think memristors are going to give rise to conferences in very nice places.
Okay. So before I open it up, I have one burning question, and I think I'll pick on Stan for that. What is the commercialization timeline?
All right. Well, that's always interesting. There's two issues. One is that there's not a fab on Earth that couldn't be making integrated memristor circuits tomorrow. It's simple structures, readily available materials that are already in the fabs. So any fab could be making these circuits literally tomorrow. The problem is there's only about this many or maybe this many people on the face of the earth who actually know how to design the circuits. One of them is sitting down there and one of them is over there. So I think that the primary limitation is not necessarily, or the timeline is going to be actually getting enough people who actually know how to design the circuits to make in the first place. And so with all of that said, I'm going to sort of put my hand down and I'm going to say probably minimum 3 years, maximum 5. They'll be in the marketplace.
If you don't ask a question, you don't get to leave. Close the doors, right? Yeah, go ahead.
I don't know that we clearly see how we do it yet. I mean, the biggest problem we have with attacking digital logic right now isn't density or scaling. It's the power density, right? And And unfortunately, the the memristor still does require driving lines and wires, and that's what consumes most of our power problems right now. Before you can say for sure, you'd have to actually see what is the circuit you're going to build, what are all the circuits around it that's going to be, as you alluded to, Stan. You have to see how the drivers and things are there, the muxes, demuxes, all of that. And my concern would be that to drive very small nanowires, it's quite resistive. It does consume a lot of power, especially if you're still operating at a volt or two. That's our biggest problem with CMOS right now, is that we're still at a volt, and until we get below a volt, making things smaller doesn't help us much. We already today trade off our density for speed and power, because we could make them denser in the current generations, and we choose not to in some cases because we couldn't handle the power that would come along with that. And that's mostly a voltage statement, that you can't get below a volt yet. Now, to the extent that memristors can go down to sub-volt ranges and have them much lower voltages driving wires, therefore could take advantage of the density, then that could be actually a way that they could make progress there.
I partially agree, but only partially. Of course, the power density is the major issue today. And the way it's handled today in processors is that you don't accelerate or you don't increase the frequency, the clock frequency anymore. So you have to think of how to either decrease it or switch off certain parts of the field. On the other hand, the memristive systems which we discussed today have the chance that in some cases you can have smaller wires, shorter wires. And then if you have shorter wires, just in the same ratio, you cut down the load capacitance. And then you save energy. In addition, especially the electrochemical metallization cells, they can be driven at some few hundred millivolts. And that's certainly below the level which you need for CMOS. So, and since it's CV square, you save with every part of the voltage, you can save energy.
So if you can get the voltage down, I'll buy the argument. that I would agree with.
You have a follow-up to that, or
yeah, just a follow-up.
Okay, then go ahead.
So, but if it's finally a two-terminal device, does not it look like a very leaky transistor from addressing point of view? Because if I am trying to address it using wax, it's just like having a transistor which has a huge leakage current.
So I'll have to defer this one off to someone who knows what the circuit designs are they're planning on using here. It seemed like from what they were showing, it was being utilized more as you have transistors and things driving it, and you're using this just to do your logic calculation and not necessarily using those as the drivers themselves to try and move things around.
Okay, but the wax that I use to address them, right?
Mm-hmm.
So I'm probably using kind of an interconnection to address them because it's a two-terminal device. So that looks like a leaky gate to me, right? Because I'm driving a lot of current to those points. Is that the right way to look at it or not?
Well, somebody else who knows the circuits better.
I'd like to hand it off, but yeah. No, I don't think it looks like a leaky transistor because you don't. It's non-volatile, so you don't have power flowing through it all the time. If I understand the circuits correctly, so I think the fact that it's non-volatile is really the key. You set it and then you forget it. It just sits there, and then you just pass current through to read it.
Yeah, I mean, I think that's. I mean, it's not a leaky transistor. It is a resistor, and so you're not trying to hold a gate voltage on the device. It really is just it is a dissipative element, but the fact is that you don't have any leakage current associated with it. So, I mean, from that standpoint, you save probably half the power dissipation anyway, right there from the fact that so much of the power dissipation in chips is through leakage through the thin gates that exist now. But let's just say that sort of characterizing it in that fashion, it's just too simple. That the fact is that the entire circuit, you have to look at the entire circuit issue, and believe me, it's very possible to design terrible circuits with memristors. Okay, that's easy to do. It's very easy to create a straw man where you have a circuit that will just burn huge amounts of power and be and just be very poorly performing. So what it means is that you just really have to be do a good job of dealing with the engineering trade-offs and try to hit a sweet spot in the design.
Question here. My question was, so you want to use your memristors not only as memory devices but also as logic and for computation. So these devices all have a certain wear out, so you can cycle it 10 to the 6, 10 to the 7 times, and then they all die. Is that sufficient for doing some serious logic other than a proof of concept?
It depends upon the type of logic that you're doing. If you're using this as, for example, for a field programmable gate array, for the configuration bits in a field programmable gate array, it's more than enough. If you're using it as the actual gates, logic gates, it's nowhere near enough. And so, but the issue is that this is very, very early days. I mean, the early transistors didn't switch that much, and so we're in the very, very early stages. I don't think that there's anything fundamental with the endurance on these things. In fact, I'm actually amazed they're as good as they are, given the state of the technology. Because when we test these things, we do it bare naked, out in the open air, on a bench, no packaging, no passivation. Nothing. And the fact that they're lasting as long as they are, I think is actually remarkable. So once we actually get to the stage where we are passivating and packaging, I fully expect that the endurances on these things will go up by many, many orders of magnitude.
So if you have a product in the market in 3 to 5 years, you start with the memory, or like with the whole?
Very likely it would be a memory.
Okay.
And very likely it would be something that would be a competitor with flash. And the endurances that these things have bare naked are already orders of magnitude better than flash.
Yeah. No, you.
Yes. I have a question about noise in memristors. It seems to me you have just mentioned that you want to go below a volt, and again, huge resistivity in small wires, small diameter, like long wires to diameter ratio. So at least even resistive noise would be huge. And if you go below a volt, the signal to noise ratio might be overpowering. And current digital logic already has problems distinguishing between states because of noise. So are there any thoughts on whether noise would be a huge issue in this? Or?
Noise is certainly an issue. And especially if you go to the analog ideas, then you have to take really care about that. On the digital side, you have to consider that the current, they are very short, but they are not very low. So certainly the right voltages, the right currents for any kind of the memristors will not be below 1 microamp. And then I'm quite sure you can handle the noise issue.
I'm going a little beyond the device level now, because if both a logic and a switch, and when you combine multiple memristors, you can do more functions. Is there a potential for a cellular array or ultimately a massively parallel processor potential with this, and in a smaller implementation area?
Did everyone hear the question?
Okay. Thank you. I'm KRS Murthy. I serve on the board of a memory company.
beyond the device level, because it's a logic and a switch and many other things. When you combine multiple memristors in particular fashions, you can have a cell potential to be a cell by itself, to make it a cellular array, and ultimately maybe a MPP or a massively parallel processor architecture, maybe for specific applications like video and other things, and picture processing and so on. But is there any distinct advantage of this implementation over anything else that has not happened in the industry? MPP has not really happened in the industry. You know, this probably has a higher potential. Any comments and feedback?
Thanks.
Yeah, I think this is a good point. And as a matter of fact, one of the things that I mentioned, my second set of comments, I think there are opportunities for massively parallel arrays. It's not going to be general purpose. For special purpose applications, however, vision applications might be a large class of applications that might justify fabricating a special class of processors for these kinds of applications. And I think in order to have some kind of an adaptability in these structures, if you think about cellular arrays, the way each cell connects to the neighbors, you would like to have this adjustable. And so I think
more than a regular cellular array, it's a weighted connection.
the weighted connect, I think they, no one has worked on that as far as I know, but I see some opportunities exactly in that direction.
Other questions? Okay.
Dr. Williams, so you come from academic background and a scientific background. Could you speak to the business aspects of how HP will work with other companies who, for instance, suppose there is some UC Berkeley graduate student who's interested in this topic and maybe wants to get into designing circuits. And what kind of intellectual property, patent issues or things are they going to have to keep in mind if they want to start their own company and maybe go to some fab? And would HP maybe be a company that would do fabbing of devices in conjunction with a company that did design?
Okay, wow, that's that could take us for a while. I have to see, is John still out there? I mean, do I have to? Okay, so at least the business guy left, so that means that I can. I won't suffer too many consequences. First of all, it's highly unlikely that we're going to fab these ourselves. The only fabs that we have left are making inkjet cartridges. So, in terms of the rest of the chips that we have, we are a fabless company. We do a tremendous amount of chip design ourselves. So we do a huge amount of in-house design and then have those chips fabricated in various places. So with respect to Memristor integrated circuits, you saw an example of one out on the poster out there. That was actually fabbed on a inkjet cartridge fab. But sort of the next generation is going to have to be done at a shall we say, more electronics-oriented system. And so we will be and are looking for partners, large industrial partners who have fabs or essentially foundries that we can work with for the fabbing of chips that are particularly, of interest to us. For the most part, I mean, HP turns out to be the world's largest consumer of memory chips. We buy more memory chips than any other company on the face of the globe. And so we are concerned and we are interested in the types of technologies that go into memory chips. And so whatever winds up being manufactured, we're automatically going to be the biggest customer for it. So that's part of an issue. As far as other companies who are going to be making chips, we won't be a manufacturing partner for that. But we, if it's an interesting chip, it's almost guaranteed that we'll be a customer for it. So it's in our best interests, if this is going to be a broad technology, to understand it at least as well, if not better than anybody else. I mean, that's sort of our issue right now. We don't make that many chips, but we want to make sure that we understand them as well as anybody does, so that we can actually utilize them. So that's really the issue going forward. I mean, here's an opportunity not only for us, but for the industry, and we're going to do our best to shepherd it in an appropriate fashion. We're not going to prevent anybody from working in this area. But on the other hand, it's, we're not going to be going out and bringing people in so that we can partner with them and so that we can be fabbing either. So does that sort of handle your areas?
So, how would someone who's interested in creating products using this technology who doesn't work for HP, because you're talking about like this might be the first of a series of conferences. Who should they be looking to work with, partner with? Are there people at HP that they would work with, or is it
I mean, if it's going to be a different company, it's probably not going to be working with people at HP. I mean, we have our own resources. We're not going to go out and partner with a small company. We just blatant about it. That's not in our best interest. It's frankly not in our interest at all. So it would be the standard, the standard startup type of process. I mean, there's a ton of small fabless companies out there that get an idea and get a foot in the door and start designing and making things, and 90% of them go bust and 10% of them do really well. And so there's nothing different about Memristor technology than any other electronics technology today. Practically every company is fabless in one way or another. I would say that the main difference is that if they're not taking classes from Leon, they're going to have to figure out who they're going to actually learn from to do the designs. That's really the main issue is this is a different type of device. No one has ever built, well, except us, no one has ever built an integrated circuit using these devices. So it took years for us to get to that point. I mean, it took a lot of years. So this is a path that anyone who's going to be working in this area is going to have to go down, whether it's in a small startup or in a large organization.
One question for the bio stuff, because no one's asked you a question yet, and this was really playing on my mind. I think what you said about the synergy between electronic or solid state and biological systems in terms of memristive type properties and how they could play in the future, I think that's really interesting. Could you name one or two applications or examples where this synergy could be used to do something different?
Yeah, well, one thing is learning. So adaptive behavior in simple organisms and how they learn. And so we could reproduce that in a lab. I mean, what I showed was a theory, but those things can be done now in a lab. And that is beautiful, because if you combine several of these, then you can have complex behavior that we didn't even anticipate or we don't know yet. And that could be, so if you find it, you may have the same behavior in the bio area. Spontaneous behavior, for example, in animals, right? If you combine several of these elements, you would have chaos, right? I think Leon also discussed this. But chaos is nothing else than spontaneous behavior, and you can use this to understand spontaneous behavior in colonies, right, of animals. So there are several of these concepts that memristive devices could be helpful in understanding, and now we have them, or at least we know how to make them, and we can literally take an idea from the animal world and try to simulate it in a lab.
Running out of time. I think we are, by my watch, 5 minutes over, but I'll take one more question.
So there's an integration that asks you a very, the perspective of research means perspective of science and how we approach, or is it not? But, so that we have, in order to actually reflect on research and make them applicable to daily life, we have to reflect how we approach material science. So what do we need to do from a material science point of view in order to make research more effective? Well, I guess what should be our mindset as materials engineers?
Just so that everyone hears it, the question is, what do we need to do in material science?
I'm not sure that I got every point of your question, but you were addressing material science. And okay, certainly you need to understand more details of the mechanism, every part of what happens, in order to be able to extract from this understanding more general design rules, which then allow you to have a more systematic search in the huge world of, for example, just the transition metal oxides and combination of transition metal oxides and so on. That's what we have to do. That's a lot of work ahead. Interesting work.
Okay.
From a materials perspective, what is important in the future is looking at the morphology, failure mode effects, analysis, and impact on a bigger system, and what kind of redundancy and fault tolerance one can have to really compensate for that would be a very important materials related thing. And if it's only inorganic, now I'm envisioning an organic memristor and a bio-memristor, And if that can be done, it's a different ball game altogether than simply FMEA.
You have a question? Okay. One final question.
Really, I'm an ex-SPICE guy. So in that sense, I have a question on the, equivalent circuit model for circuit design. So as of today, what's the most difficult part of Memristor to make a reasonably good circuit model, or equivalent circuit model? What's the biggest challenge of that?
Well, to my knowledge, there's only one copy of SPICE on the face of the earth that actually handles memristors, and that was actually written by Greg Snyder. And so he has his own essentially personal copy of SPICE that he has put memristor modeling in, and I think that the main problem is just getting the right mathematical model. I mean, it turns out that it's a little bit complex. I mean, I sort of presented a completely linear freshman scale model, but then I mentioned that in fact, there's actually nonlinear transport of both the electrons and the ions in the system, and so, in the end, the actual differential equation that you use, I mean, we still haven't nailed down all of the aspects of that yet, but I think that for some of the design things that Greg is doing, it doesn't have to be precise, but that's still it. I mean, we're still at a stage where we haven't nailed down every little term in the dynamics of these devices, but it turns out that knowing that these were dynamical devices and knowing that there were memristors, actually opened up a whole new window for us to understand the material science. I mean, we've been, mucking around for almost 10 years with these things, and it wasn't until we really understood that there were memristors and we had Leon's equations in our hands that we really started opening up the doors and really started to understand things in very great detail. So it turns out that that's a strongly coupled system, and there's a lot of feedback between those two. And the more we understand about circuit properties, the better we understand the materials. And that just goes back and forth.
I have to close here. Chancellor Kang gave me a tough task of having 5 such distinguished panelists and wrapping it all up in 30 minutes. So I lost out by 11 minutes, so hopefully that wasn't too bad. So I want to thank everyone, and I also want to say what an honor it is to be in your presence, Professor Chua, because not that many people invent a whole new device. There's only 4 of them, right? So. Okay, so it's definitely a huge honor. Thank you very much.
Thank you very much. Let us give a big hand. So on behalf of all the organizing team, I'd like to sincerely thank you for being here. Whole day. It was a really long day. I hope you appreciated all the speakers and the poster presentation and the wonderful panel discussion, and learned something throughout the day. And thank you for being here, and I hope you have a safe trip back home. Thank you for being here. And one additional information is that there were many people asking whether this symposium will be webcasted today or not. We couldn't do that, but we will put some material on the website where you made the registration. So that's memristor.ucmerced.edu. We'll try to capture all the information and have it available, everybody in the world for that matter. Yeah, thank you. Thank you.